Here we go. Okay, so this lesson is about light clients and bridges. This is the last lesson of the module. Well, I should say like the last lecture of the module. Hopefully we still learn some lessons with the coding part. So when I went to prepare this, I was not an expert on light clients. I guess I'm still not an expert, but I know a pretty good amount at this point, and a lot of it came from talking to this guy, Pierre Krieger. He goes by Tamaka on GitHub, and he has this logo. And I said, Pierre, tell me everything you know about light clients. And he said, what can I say? It's a client, but light. And I was like, okay, great. Now I know about light clients, and proceeded to do my own research. So the problem is that running a node is hard, right? It's hard. We all experienced it just now. It took us nearly an hour to get a node set up. In reality, it actually can be pretty hard. You know, if we were going to run a production node, we would have to have a lot of like failover infrastructure, and we would have to have a lot better bandwidth and a million other things. So there are some challenges. The ideal, I would say, is that if you want to interact with the blockchain in a trustless way, you should run your own node. Some communities are a lot better about enforcing this than others. Not enforcing, but like promoting and encouraging this than others. So the best example I know is the Monero community, where everybody's always encouraging you run your own node. And when someone asks hard enough, like, is there just an RPC node I can use? They're like, okay, fine. If you want to do it the insecure way, here's an RPC node address. But just know this guy's probably going to lie to you and censor you. Run your own node. Other ecosystems don't have that as such a strong value. Like Ethereum, for example, I think they're getting better, but they also have all this public infrastructure where you can just connect an RPC node for free of money. So the reality is that it takes a lot of disk and memory to run a node. You know, our blockchain's only 100 or a couple hundred blocks long. It's not such a big deal. Those blocks are mostly empty. But a real blockchain network, it takes a little bit of more. It also takes some know-how. Like we all learned a lot from that activity, even me. And another criticism that people have about running their own node is that they don't need it all the time. You know, maybe they check their balance and send some transactions like once a day or once a week. And so there's a lot of overhead of keeping your node online all the time. So while it really is good for you personally and for the network to run your own node, there are also some legitimate criticisms about why you might not want to go to all the effort to run your own full node all the time. So one solution is RPC nodes, aka use someone else's node. But there's problems with RPC nodes. One is that they might spy on you. We learned recently that Infura spies on you. They log at least your IP address and probably a lot more stuff about you. So at minimum, there's a privacy concern. They might also censor you. If you try to send some transaction through Infura, they might not send it. Do they censor Tornado Cash? I don't know either, but I wouldn't be surprised, you know, and just because they don't now doesn't mean they won't in the future. They might also lie to you. They might tell you like, oh yeah, your balance is X, and actually it's not, and you have no way to verify that. And at the end of the day, they really might even steal your girlfriend. These are just really bad people. You don't want to trust RPC nodes, right? That's not the way we want to go. So the alternative, well, the one alternative is run your own node. That's always an option. The alternative to try to make progress against some of those legitimate concerns while also maintaining a little bit more trustlessness and sovereignty is to just lighten the load up a little bit. So imagine you want to run a node from your phone or a microcontroller or maybe even inside of a web browser on a low power like Chromebook or something. These are all pretty resource constrained environments. But it's also realistic because you can imagine like you have some kind of security camera that has a Raspberry Pi in it, and you want it to, the moment that it sees some weird activity, you want it to submit a transaction to the chain so that everyone in the world can attest, like, this camera is claiming something weird happened at this exact time. And then if you need to prove it in court, you can. It was attested to globally, and it's part of our shared story in our state machine. Or you can imagine something a little bit more practical. Maybe you just have a phone and you want to like tip your Uber driver, and you don't like have a server to start an Ethereum node to send some ETH to this guy. Maybe you just want a node to run right here on your resource-constrained mobile phone. And it has even more constraints than the like disk and memory ones I talked about. It's also resource-constrained just in terms of like energy and battery. So we have some like legitimate use cases for wanting to squeeze nodes into like tighter environments than you would like typically be able to fit a full substrate node or like Geth node or Bitcoin node. And so the solution, I guess I didn't actually put it on the slides anywhere, but the solution here is this thing called a light client or a light node. And I'll just tell you some of the things that they do and don't do. I had a slide earlier this week about like the things that a node might do, and I said some nodes do every single one of these jobs. They're like called archive nodes basically, and some nodes do a lot less. So a light client doesn't sync the blockchain. It doesn't even execute the blocks. Of course, it can't execute the blocks if it doesn't sync them. And it might seem like those are pretty core ideas, and in some sense they are, but it does do the core of the core, what I call the backbone of the blockchain. It syncs the headers, the header chain. So if you remember, the headers are actually what has the cryptographic hash linking between them, so it can verify that the chain is actually unbroken and it has the proper hash link. It also checks the consensus rules, so if you have a proof of work chain, it makes sure that the hash is low enough. If you have a proof of authority chain, it makes sure it was signed by the right person or one of the right people. And then also, just a reminder, proof of stake also counts as proof of authority, so it checks that as well. It doesn't maintain state for sure. If it's not even executing the blocks, it can't compute the state in the first place, let alone sync it. And then some light clients will maintain a transaction pool, others won't. And some will maintain like a kind of half transaction pool where they allow their own user to send in transactions and gossip them out to other nodes, but they don't participate in like actively gossiping other people's transactions around the network. And so the basic idea here is that the light client does the minimal viable amount of work necessary to interact safely with the blockchain. So the idea goes all the way back to the Bitcoin white paper, the very first blockchain. This figure comes straight from the Bitcoin white paper. And at that time, they were known as SPV clients, or Simplified Payment Verification clients. And so you can see we have a chain of block headers here. It's not the full block body, as I mentioned. It doesn't have all the transactions in it. But you can imagine that maybe you want to query your light client and say, hey, light client, can you please confirm for me that I actually received this payment that, you know, whoever, Joe, says that I received? And so what you do is what the light client does for you is it says, okay, I already have the block header. I always maintain those. And the block header has a Merkle tree root of all the extrinsics, all the transactions that are in this block. So what it does is it calls up one of its peers, a full node, and it says, full node, please provide for me a proof, a Merkle proof, that this transaction is actually in the block. And so maybe this is the transaction that I care about from Joe, and the full node gave me enough data, enough sibling nodes, just like the thing you guys implemented in week 1's assignment, to show me that indeed this thing is actually in the block. And now I know that payment from Joe came in. And I didn't have to trust anybody for it. Now, I did have to rely on a full node to at least give me the data. If no one's willing to give me this proof at all, then I'm kind of out of luck. But as long as anyone's willing to give the data, I don't have to trust that it's correct. I can verify that it's correct. So in Bitcoin, this is all it was. In Bitcoin, you could only verify the presence of a transaction in the chain. Imagine if it's the other way around. You want to say, I want to confirm that my payment to whoever, my electricity provider, actually cleared. It actually went through. It's actually in the chain. And so I do the same thing. I see that my transaction to my provider is in the chain. I can't confirm that they still have the money. They might have already spent the money. And in Bitcoin, that's just the state of the world. You can only confirm the presence of a transaction, but nothing about the state. But in other blockchains like Ethereum or Polkadot and most others actually, you can, because most blockchains not only have this transaction Merkle root, what else do they have in the header? The state root, bingo, yeah. So where most chains, you can do the same thing for the state. Okay, go ahead, run the mic to him.
How do you know in which block there is a Merkle root for your transaction? I mean, because the transaction is in the body, yeah?
Yeah, right.
How do you know that?
Yeah, is it this block or this block or this block or any more in either of the directions?
But you have only the headers, yeah?
Yep. So as the light client, you don't know. What you do is you call up a full node and you say, hey, full node, please tell me about this transaction hash. And the full node knows where it is and produces the proof for you. Great question. And same exact thing with the state proof. Actually, I just realized I had the answer on my slide. The state root actually helps a lot. So Bitcoin doesn't have that feature, but most chains do. So you can do this for states or extrinsics.
To compute the hash of the block that you call for the proof of work, is it on the header or on the whole block?
Yeah, the proof of work happens on the header. Yep, not on the whole block.
It's always on the header.
Always on the header, yep.
Okay,
Exactly right. Great question. Yeah, because if it happened on the whole block and I'm not syncing the whole block, then I couldn't check the proof of work. Yep. And honestly, it's the same thing for proof of authority / proof of stake too. The signature that the authority puts is signed over the header. So the consensus stuff always happens at the header level. It's just less data that way. And honestly, it enables this whole light client thing. We saw what the light client still does. We've already made it a lot lighter by not making it do all of this stuff, but it still does have to do some stuff, syncing headers. And syncing headers takes time. It takes a lot less time than syncing blocks, but it still takes time. So imagine, maybe syncing headers reduces the time of syncing your chain from hours down to like 1 or 2 minutes. Well, that's a huge improvement. Great job. But 1 or 2 minutes is definitely still longer than your Uber driver wants to be sitting around waiting for your tip to come through. So we might even want to do better. So the first thing, like I said, is we only sync the headers. That helped a lot. Another thing that you can do is you can actually have a checkpoint block in the code. So when you download the code of the light client, it might say like, this one block at height 10,000 has this particular hash. It's widely agreed by the network. And so when you start syncing, you can just start syncing at this checkpoint. Now, there's a little bit of trust there. That's not totally great, because if the maintainer of your light client ships a checkpoint on some side attack chain or some fork chain, then you might be out of luck by syncing the wrong chain there, okay? So know that checkpoint blocks do introduce a little bit of trust, but the counterpoint here is that you already trusted these people to write the whole light client code. So like, if you don't trust the people you're downloading the light client code from, you probably shouldn't be running their code on your device in the first place. That's kind of the point and the counterpoint. Now there's another strategy that you can take, which is called warp sync. And warp sync is useful in, actually, let me make this point first. If you have a simple proof of authority chain where you have the same authorities forever from Genesis until whenever, you could just download the latest header and check that the proper authorities have signed it and that you have at least 2/3 of them signing, actually at least greater than 2/3, and then you know that you're good. You know that that one's final. So that would be really good. That's O of 1 sync time for the headers. But in reality, our proof of authority chains are typically proof of stake chains where the authorities are changing based on stuff that happens in the state machine. And so you can imagine that like every 20 blocks or every 100 blocks, or the way Florian phrased it the other day, once per epoch, the authorities are going to change. And so if you only know the authorities from Genesis, they're not the same authorities that are going to be signing the finality certificate for the latest block. So the way warp sync works is instead of downloading all of the headers, it downloads one header per epoch. It downloads the one where the authorities changed, and what it does is it makes sure that the old authorities finalized the thing that says, here's the new authorities. And once you know the new authorities, you make sure that they finalize the thing that says, here's the even newer authorities. And you do that all the way until you're near the tip of the chain. And by doing that, you don't have to download the entire history of the header chain. You just download an even more minimal amount of information. So these are strategies to improve the sync time down from days or hours down to minutes, which we do by only syncing headers, and then from minutes down to seconds, which we do by a method like this or other methods. Okay, so the last thing I want to talk about is self-defense in your light client protocol. So if you're a light client, we saw that there's some relationship that you have to full nodes. You already have to have a full node to ask for these state proofs or for these extrinsics proofs when you need them. And the other thing I want to say is that you shouldn't just communicate with one or some small number of full nodes. You should really stay in the full gossip protocol of the network. What we saw previously is that if more than 2/3 of authorities sign a block, you can consider it finalized. Typically, when we have finality, we say there's some latest finalized block, and we'll never reorg deeper than the latest finalized block. But if enough nodes are Byzantine, we can have 2 competing blocks that are finalized. Now, we already talked about how that's not going to happen in the main network protocol, because the moment that happens, it's provable. It can be reported back to the state machine, and these guys are going to be slashed. They have an economic incentive not to misbehave like that. They have an incentive to follow the protocol properly, and that's why we typically assume that we do have at least greater than 2/3 nodes honest. But if you're not in that gossip protocol, and some light client, some full node colludes with some other full nodes, and they say, we're going to finalize an alternate chain, and we're going to do it on the lowdown, and we're only going to send it to this light client guy, this person who's running the light client. because that light client guy is not in the gossip protocol, and they're not going to report us back to the main chain. They're not even going to hear about the main chain, and we're going to get away with the crime. That's the danger, okay? So when you're running a light client, you need to make sure you're in the gossip protocol so that you can hear about the two conflicting chains and report them back to the main chain and get the bad actors slashed. So when you run a light client, you don't want to do it super naively, because if you do it that naively, you're ultimately trusting that the peer or small number of peers you're connected to aren't going to collude and lie to you.
So what does it mean being in the gossip protocol? Because if I understand correctly, you're connected to an RPC node as a light client, right?
So it may be an RPC node or not. This is a great thing that I haven't actually really explained as thoroughly as maybe I should have. There's multiple ways you can connect to a node. One is as a peer, and when you're connected as a peer, you do things like gossip blocks or headers or transactions. Now, light clients obviously don't gossip full blocks. I think I did make that point well. But they're gossiping all of these headers and this like finality proofs and stuff. The other way you can connect to a node is the way that like our user interface, Polkadot.js, connects to a node, and that's through the RPC. So what I'm saying here is make sure you're let me show my graphic. Why didn't I show that yet? Make sure that you're actually connecting to enough peers that you see the full picture of the network so that you can rat people out when they lie to you. Because without that, they have no incentive to remain honest and follow the protocol. So that's it for light clients. I want to talk about bridges next. That's the second part of this. We're not quite halfway, but we're getting there. Okay, so that's a bridge. Any questions? So a bridge is basically like a transport layer between two independent consensus protocols. So you can think about like Bitcoin and Ethereum, or you could think about Dogecoin and Polkadot, or something like that. Two totally independent consensus systems that have like different validator sets, or different proof of works that they're orthogonal to each other. And so while they don't rely on each other in any way for consensus information, it might be useful to be able to like move an asset from one chain to another, or like prove that you own an NFT on this chain in order to unlock a capability in some game on this chain, or any number of things you might dream up. And they're named the source chain and the target chain. Okay, so the target chain gets to learn information about the source chain through the bridge. So that would mean like maybe you can send money from the source chain to the target chain, or prove that you own an NFT on the source chain and use it in a game on the target chain, or something like that. Okay, so when you want to talk about a two-way bridge, most of the time in reality we typically think about two-way bridges. Like I can send my coin from Bitcoin to Ethereum, but then later maybe I want to send it back to the original Bitcoin chain. So what's really happening there, at least the way we conceive of it, is that it's two different one-way bridges. You can almost think about it like a highway bridge, where there's like one lane going this way and another lane going back the other way. Okay, so here's the problem. Source chain reorgs. Imagine that this is the source chain up top. I should have had arrows here, but whatever. So here we've got like Genesis is somewhere back here, and our chain progresses to the right. And at some point, we relay some information from this block over the bridge into the target chain. And the target chain maybe takes some like side effects, lets us use that thing in a game, or lets us like trade our bridged asset on a DEX, or any number of things. And then the source chain reorgs. It's basically like we could execute a double spend, but the victim isn't someone selling us their motorcycle. It's something happening on chain in a different chain, in a totally orthogonal consensus protocol. So this is the like main problem in bridge design that we need to solve for. We want to be sure that like before the target chain acts on any information it hears from this block, that we're never going to reorg away from this block. So do any concepts come to mind that might help us with this? Yeah, I heard someone say it, finality. Yeah, at a high level, we want to make sure that this block is finalized. So we're going to dig in, because don't worry, there's a lot of tricks that might happen. So there's two bridge models. There's the trusted bridge. The classic example is the WBTC Foundation. That's the wrapped BTC Foundation. And it's basically a group of people who got together and said, hey, there's value in letting people move their Bitcoin tokens over to the Ethereum network. And the way it works is that the WBTC Foundation has a Bitcoin wallet, and you send your Bitcoin to those people who work at the foundation, and once they're convinced that they really own those Bitcoin, then they mint you a token on the Ethereum network, on the target chain. It's called WBTC, or wrapped BTC. And it's, for those of you who know about like ERC20s, it's an ERC20. It's just some token. You can like do whatever you can do with any other kind of token. And then maybe at a later date, you use the other lane of the bridge and you send your WBTC back to the same folks who work at the WBTC Foundation. And once they're convinced that they actually have that money, then they send the original Bitcoin out of their wallet back to your wallet or wherever you tell them to send it. So what's the problem with that? Yeah. The trust, right? Like everybody probably knows it already. Like I described the protocol as like you give them the Bitcoin, they give you the wrapped Bitcoin. But the other thing that could happen is you give them the Bitcoin and they say, get the hell out of here, I never got your Bitcoin. And then that's the end of the story. Now in practice, the WBTC Foundation seems to be doing a great job. I don't know of them scamming anybody, but that doesn't mean they won't scam you tomorrow. Or maybe they're not even malicious, maybe they just accidentally lose control of their keys and they're the ones that get scammed and therefore you get scammed on, as a downstream side effect. So something interesting that I want to observe about doing this with Bitcoin is that, you guys said and observed like finality is going to be really useful here, but Bitcoin only has probabilistic finality. So the WBTC Foundation has to make a judgment call, just like everyone else who ever receives a Bitcoin has to make a judgment call. They have to say, when am I confident enough that I really have this Bitcoin before I send the tokens over? Okay, so that makes building any kind of bridge from probabilistic finality like a little bit hard and a little bit dangerous. We're going to try to do a little bit better once we have provable finality with like Grandpa or Tendermint or any other Honey Badger BFT, one of these BFT-style provable consensus protocols that we talked about. Okay, right. So the next kind of bridge is the trustless bridge, and obviously that's the kind that we like want to build. That sounds a lot better, sounds a lot more in line with the ethos of the ecosystem. So let's dig into how those designs work. Let me make sure I didn't miss anything. Oh yeah, just the point that like if you're working with a trusted bridge, it doesn't have to be quite as naive as what I just described. It might be built around like a multi-sig or something where like 5 out of 7 people have to be compromised before you get totally scammed. But like that doesn't really fundamentally solve the problem. It just kind of makes it a little better. Okay, so the most trustless way to interact with the blockchain is to run a node. We talked about that already. It's true for individuals, and it's also true for other blockchains. So if you look back to the figure of the bridge here, you can almost think of the target chain as being a user of the source chain. In the same way that a human might be a user of the source chain, the bridge is relying on getting some information from the source chain, and we want it to be able to do that in the most trustless way possible, and that's not by trusting the foundation to always tell you the truth. We just learned a technique to interact with a blockchain relatively trust-free, and it worked well in a low resource environment. And it turns out that running on a blockchain is an extremely resource constrained environment, just like your Raspberry Pi and just like your microcontroller. So the secret or the key observation to building a trustless bridge is that a trustless bridge is actually just a source chain light client running on the target chain. So in the same way that I said, you can use a blockchain relatively trust-free from a light device like your phone by running a light client on it, the exact same thing is true for a target chain. If your target chain wants to interact trust-free with the source chain, it should run a light client for that source chain. And so putting the light client as on-chain logic is sort of like the key fundamental observation in building a trustless bridge. There's a lot that can go wrong after that, but I'll just like let that sink in for a second. You run a client for the source chain on the target chain. Okay, so the earliest example that I know of this is this project called BTC Relay. I don't know if the term bridge had even been invented yet, and I don't know if people immediately realized that what they were doing was running a Bitcoin light client on the Ethereum chain. But in the end, that's what it was. So I cribbed this figure directly from their website. I didn't make it. Probably wouldn't look this good if I made it. But what they're showing here is that you have the Bitcoin blockchain, and these are the blocks. Actually, they're the headers. And there's this role of people called a relayer. And what the relayer does is watches the Bitcoin blockchain, and every time a new header comes to the Bitcoin blockchain, they submit that header as a transaction on the Ethereum blockchain. And so there's like some light client logic running as a smart contract on the Ethereum blockchain that makes some minimal light client style checks on the Bitcoin header. It makes sure that the proof of work is valid. It makes sure that the cryptographic link to the parent is valid. And then it stores all of that information on the on the Ethereum chain. And so the last point I want to make about BTC Relay is that there's no application built on top of it like by the BTC Relay folks. All they're doing is building this bridge where the headers for Bitcoin, the source chain, are tracked in Ethereum, the target chain. And then it's up to you, the contract developers, to build interesting stuff on top of it. So you build another smart contract that uses this data from the BTC Relay bridge to do interesting things like, you know, mint a wrapped version of the token or use the NFT in a game or whatever else. Yeah.
After enough headers, enough blocks, isn't the chance of it being a fork that will get reorged basically zero? Like it's statistically almost impossible, so where's the safety risk there?
You're thinking about it exactly the right way. The deeper the header is, the safer it is, and so at some point I'm going to consider it safe enough, and not everyone's going to agree on where the line for safe enough is, and it might be different for applications. So like, I can't give you an answer that says like, this is exactly what safe enough is. All I can say is that for some applications, maybe 6 blocks is enough. For others, maybe 10 blocks is enough. There's always some small but non-zero chance that you're going to get reorged even deeper than that.
I think the chance is up to like how much one is willing to spend. Like, I think or I look at it this way, that after like each block that passes, the cost to revert this is higher. So it's a matter of like how much energy is going to put into Bitcoin to create a new fork now. And you know, at some point that number gets so high that, I mean, I would say it's impossible. I would say it's infeasible.
Yeah, I would say your understanding of the protocol is spot on. There's like nothing that I want to like change or correct about your understanding. It sounds like, you know, you're saying that for many applications, once the block is 10 blocks deep, you would be happy to use it on the Ethereum side, and that's great. BTC Relay would be very useful for you, just like it was for a lot of other people. Yeah, good. Okay. So let's talk about bridge design challenges. We sure don't want that to happen to our bridge. Okay, so peers. I showed the slide with Willy Wonka previously saying you have to stay in the gossip protocol. You want to be connected to a lot of peers because otherwise some authorities could collude together, finalize a competing chain that isn't the real one that the main source chain protocol sees, and convince your light client that it's the real one. And all we have in our trustless bridge is a light client. But when you're running inside of a blockchain, like inside of Ethereum or inside of Polkadot or whatever other blockchain, you don't have like, you know, network I/O. I can't like reach out and establish a peer connection over to like the full nodes on the source chain. So we have to somehow like replicate this phenomenon. And so this is the role of the relayer. So the relayer existed in BTC Relay. That's like these little birdie guys that take the, you know, headers and submit them in transactions to the light client. So these replace part of the role that a peer would normally take. And the relayer is a trustless and permissionless role, which is really good. All they have to do is relay the headers so you're sure the headers get in. Now, I guess basically the constraint is that you need at least one honest relayer. If no relayers are honest, they might like fail to relay at all, or they might choose to collude and like only relay the attack chain. But the really good news is that when you have these roles where you only need one honest one, it's super easy to guarantee, because the worst case scenario is that you look out there and say, okay, there's 150 relayers that I can choose from, and they all look sketchy. I don't trust any of them, so I'm just going to run my own. When it only requires one honest one, you can totally seize your own destiny and just run it yourself, and then you don't have to worry. So that's a good thing about the relayer role. Yeah, I don't think I had anything else to say there. Okay, so we talked about how the relayers bring the source chain headers into the target chain, but we don't want to neglect incentives, because as the meme here says, like, you could have this bridge design that's super cryptographically linked. It uses a very good light client protocol, but we forget about the game theory, and Achilles gets shot right in the heel, and you know that's the end. So imagine we have the source chain over here. And imagine that we see a finality proof. This block has been signed by enough source chain authorities, and some relayer has taken this block and submitted it as a transaction into the target chain. The naive thing to do would be to say, okay, I have a finality proof. That's great. I can trust that block header immediately. It's finalized, right? What could go wrong? Well, we already learned what could go wrong. The authorities of the source chain could be colluding on the side to finalize this block, but not ship it out to the main source chain. Maybe they don't send this to all of the full nodes and the other authority nodes in the source chain. They only relay it over here to the on-chain light client across the bridge. If the bridge immediately starts acting on it, the bridge doesn't have a moment, it doesn't have an opportunity for some other honest relayer to say, whoa, 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 wait a second, I'm listening to the main source chain protocol, and I saw this block, which was also finalized. So we had a safety fault of some kind, okay? So the first thing you know is that the target chain needs to wait. Even when it has a finality proof, it needs to wait to make sure that it doesn't see an also finalized conflicting block at the same height that's also finalized. And so if it sees that, let's say we add in our delay, we're going to wait some 10 minutes before we actually use this block, even once it has a finality proof. What should the target chain do when it sees the conflicting finalized block? What would a light client do? Yeah, report it. That's right. Narc them out back to the source chain, get them slashed. That's the whole point of the slashing mechanism. Since there is slashing on the source chain, the validators over there are incentivized to behave properly in the source chain protocol, but they aren't necessarily incentivized to behave honestly when they're talking to external entities like separate consensus systems. So while the relayers act like peers bringing information from the source to the target chain, you also need someone who's going to be willing to take information that the target chain sees and report them back to the source chain so that they can get in trouble. And that role is often called as fisherman. I just realized I kind of skipped some slides here. Okay, so you add a challenge period, and then you have two options. You can add the fishermen, which are the recursive relayers, and that's pretty good, right? Because then you take the information that was seen on the target chain, you relay it back, and you get them slashed in the source protocol. The problem with relying solely, there's two problems with relying solely on fishermen. The first one is that the target chain is kind of not taking care, not watching its own back. It's relying on the source chain to actually slash the validators, and if for some reason the source chain chooses not to, then the security guarantees affect the target chain as well. The second problem is even if the source chain is perfectly willing to slash when they're supposed to, the fisherman incentives are not really great. So imagine you have some healthy ecosystem where there's lots of fishermen watching, waiting to report bad behavior back to the source chain. Well, the validators who might be trying to run this attack, they know that. They know that there's lots of fishermen out there, and if they try to do the attack, they're going to get slashed. So they don't do the attack. Well, that seems great, except if no one's ever doing the attack, then the fishermen are never getting any rewards, and so then there aren't a lot of fishermen anymore. And then the attack becomes feasible. So there's this weak problem around weak incentives for fishermen. Although a lot of bridges do rely solely on fishermen, and in practice it often works well enough. But this is the kind of Achilles heel you need to watch for. You need to be sure that there are fishermen out here willing to do this. Do you want to speak? Oh, okay. So there's a second option, which is that you can actually stake the relayers on the target chain so that they can be slashed on the target chain. So that way, the moment that the target chain knows that there's been one of these safety faults, the person who relayed that block over there, the false one, the one that wasn't accepted by the main source chain protocol, these relayers can actually be slashed on the target chain. And that way, the target chain is kind of taking responsibility for its own safety. It's a little less ideal in some ways, though, because what used to be a role, this relayer role, it used to not cost any money. You could just do it for yourself anytime you want. Now there's a barrier to entry. Now you have to actually put up some stake to be a relayer. And you know that there's some risk that it'll get slashed, and now you have to start paying your relayers staking rewards to incentivize them to have stakers. Okay, let me pause there.
Yeah, these weak incentives occur in different contexts as well. In 2020 when the Make a DAO Black Thursday happened, I believe that was because this was before MEV had a lot of traction and stuff like that, and so Make a DAO was just running all of the liquidation bots or whatever, or using their software, and so no one else really ran them because everyone just thought Maker would run them, so there's no point. And then when Maker's software didn't account for a certain edge case, then there was no one running them, and people were liquidating ETH for liquidating DAI for zero ETH.
Yeah,
So
yeah.
yeah,
Yeah,
it's like I
great
think
point.
like
Great
anytime,
observation.
yeah, anytime you need to incentivize like people to, like EOAs to interact with a chain in certain scenarios, like, yeah.
Yeah, great. This is my new figure of the multi-chain application stack. So I showed you in my very first lecture this stack where you have like a UI and then a dApp, and then it runs on a blockchain instead of a central server. But now we're talking about applications that might span multiple chains with bridges in between them. You have at minimum the source and target chain, and in some ecosystems like Cosmos, you have this very complex network of bridges between a whole bunch of different chains. And so what you see is that there's a bunch of different blockchains in the bottom layer. And not all blockchains have the same security, and they don't all offer the same like quality of block space, I guess is one good way to say it. And so the point that I want to make here is that whatever quality block space you need or whatever security guarantees you need for your application, realize that your application is only secure as the weakest of all of the block space providers that you're buying from. In the same way as like your pizza is only going to be good as the crappiest ingredients that you put into it. What we've talked about is kind of like the minimal bridge design. It's sometimes called a header relay or like the trust layer or the transport layer. Just like it was the case with BTC Relay that it's up to ETH contract developers to build something interesting on top of the minimal bridge, that's going to be the case wherever you have a bridge like this. So if the thing that you build requires some state from the source chain, it's almost never going to be the case that your application only requires a header. Like headers are just cryptographic witnesses. You're probably going to want some state. So your application is going to require a state proof from the source chain in the same way that like when you're using your Light client, it requires a state proof from a full node. You might have an application where some part of it is really important that it be secure, like maybe you have some publishing platform and you really want to make sure you have good security there, so you build that on this chain, but then there's some social feature about like liking other people's published documents, and that's not really as security critical, and so maybe you build this on the weaker but more affordable chain on the lower quality block space. All right, that's the end of my slides.